Leetcode 410, split array largest sum. Split the array into k contiguous subarrays and minimize the largest sum of any subarray. Here nums is 7, 2, 5, 10, 8 and k is 2. Example splits are not the answer, we return a number. One split gives 7 and 25, largest 25. Another gives 9 and 23, largest 23. The best split gives 14 and 18, largest 18. The answer is 18. Approach: binary search on the answer plus a greedy check. Variables: we use a lower and upper bound for the answer, and a guess in between. For the check we keep a running sum of the current subarray and the number of subarrays we've started. Steps: we binary search on the answer. The lower bound is the largest single element, the upper bound is the sum of the whole array. For each guess we ask, can we split into at most the allowed number of subarrays so no subarray sum exceeds that value? To check, we scan left to right and start a new subarray only when adding the next number would exceed the guess. We count how many subarrays we need, and if that is at most the allowed number the guess works. If it works we search for a smaller answer, otherwise we search for a larger one. We return the smallest guess that works. We'll solve this a different way, close to a real-life example. You already know boundary binary search, here we use it with a greedy check. Imagine the array as a list of weights, and k as the number of buckets. Each bucket is one subarray we split into. We'll represent subarrays as buckets, here k is 2, so we have 2 buckets. We can put these weights into the buckets in many ways, but each bucket has a weight limit, call it x. We want the minimum x such that after putting all weights in, the heaviest bucket is as small as possible. In other words, find the smallest weight limit so that we can fit all weights into at most k buckets. Put 7 in the first bucket. Capacity was 18, now 18 minus 7 is 11. Put 2 inches. Capacity 11 minus 2 is 9. Put 5 inches. Capacity 9 minus 5 is 4. We can't fit 10, so start a new bucket. Second bucket, capacity 18. Put 10 in, capacity left 8. Put 8 in, capacity 8 minus 8 is 0. All weights fit in 2 buckets. This example says the minimum weight limit we need is 18, one bucket has some 14, the other 18. So the heaviest is 18. Is that really the minimum? We'll check by trying different limits. This process we just did is in fact the check method used in boundary binary search. We won't explain it again on the slider page. Let's try a few values of x and see what works. If the weight limit is 1, we can't put any weight in any bucket, every weight is greater than 1. So x equals 1 doesn't work. If the weight limit is 8, we can't put the weight 10 in any bucket. So x equals 8 doesn't work. Let's run the check method on this now. Put 7 in, capacity 10 minus 7 is 3. Put 2 in, capacity 3 minus 2 is 1. We can't fit 5, so start a new bucket. Second bucket, put 5 in, capacity left 5. We can't fit 10, we'd need a third bucket. With weight limit 10 we need more than 2 buckets to fit all weights, so x equals 10 doesn't work. Let's try a larger limit. If the weight limit is 40, we can put all weights in a single bucket, the heaviest is 32. So 40 works, but it's way above the minimum 18 we're after. We want to try different weight limits and find the minimum x that works. What range should we search? Call the bounds low and high. We can't go below the largest single weight, or that weight won't fit. So low is 10. We never need a limit above the total weight, that's 32, so high is 32. Do we need to try every number from low to high? No. This is where boundary binary search comes in. We binary search on x. The teal segment is our range from low to high. At each step we take mid and run the check we already described. If check is true we shrink from the right, if false, from the left. The smallest x for which check is true is the answer, 18. Step 1, low 10, high 32. Mid is 21. Check of 21 is true, so we set high to 21. Step 2, low 10, high 21. Mid is 15. Check of 15 is false, so we set low to 16. Step 3, low 16, high 21. Mid is 18. Check of 18 is true, so we set high to 18. Step 4, low 16, high 18. Mid is 17. Check of 17 is false, so we set low to 18. Now low equals high, we stop. The answer is 18, the smallest weight limit for which we can fit all weights in at most k buckets. When k equals 1 we have only one bucket. All weights must go in that bucket, so the minimum largest sum is the total sum, 32. No binary search needed. When k equals the size of the array we have one bucket per weight. Each bucket gets one element, so the minimum largest sum is the maximum element, 10. No binary search needed. So we only need binary search when k is strictly between 1 and n. N is the length of the array, S is the sum of nums. We do O of log S binary search iterations, each iteration runs the greedy check once, which is O of n. So total time is O of n times log S space is O of 1, only a few variables for the greedy check, no extra arrays. Pseudocode for split array. Main function, set low to max of nums, high to sum of nums, binary search while low is less than high, for each mid, if we can split with at most k subarrays and max sum mid, shrink from the right, else from the left, return low. Can split uses capacity, start with one bucket and capacity equal to max sum, for each weight, if it doesn't fit we start a new bucket and set capacity to max sum minus the weight, else we subtract the weight from capacity. Low is the maximum element, high is the sum. The answer is in this range. While low is less than high we haven't found the minimum yet. Mid is the middle of the range. If we can split into at most k subarrays with no subarray sum greater than mid, then the answer is at most mid, set high to mid. Else we need a larger limit. Set low to mid plus 1. When the loop ends, low is the minimum largest sum. Helper can split, given nums and max sum per bucket. One bucket, capacity starts at max sum, full. Loop over each weight. If this weight doesn't fit, weight is greater than capacity. Start a new bucket, count plus 1, capacity is max sum minus this weight. Else. Put the weight in, subtract it from capacity. Return the number of buckets needed.